Oh, hi. Didn't see you there. While you're here, let me ask you two questions. What is superstring theory, and why is it so important? Let's talk about it. Everything is made of atoms. Most of us know that. Most of us also know that atoms are made of electrons, neutrons, and protons. But let's go deeper than that. Here we find quarks, but the real question is, what are those made of? Theory suggests that these are made of incredibly tiny strands of energy near infinitely fluctuating. Here's an analogy brought forth by Leonard Susskind about how strings act from his book Black Hole Wars. Let's say we have propellers on a plane. When they're moving, it's hard to see the individual propellers. All we usually see is just a hubcap. One way to see the individual propellers is to use a high-powered camera with a fast shutter speed. Now imagine this. There's a set of smaller, even faster spinning propellers on the end of those propellers. Obviously, we need a more powerful camera with an even faster shutter speed. Now we can see those individual propellers, as well as the original ones. Now imagine this goes on for infinity, a set of smaller, faster propellers on the end of each of those propellers, and on and on and on. Strings are similar. Strings fluctuate, but if you use a high shutter speed camera, theoretically, you could see that each of those sections of the strings also fluctuate at a higher energy level. Sections of those sections also fluctuate at an even higher energy level if you observe them with a higher shutter speed camera. But why are strings so important? It's the unification of physics. We have known about different forces for a long time. We also know how many of them work. But the problem is, they've always been separated, and we don't know why they work the way they do. Let's start with a little background to why it's so important. Back in 1919, there was a physicist named Kaluza who suggested there are more dimensions than the three we know: up, down, forward, back, left, and right. But even before that, in 1915, Einstein published the discovery that the force of gravity worked in warps and curves, in the medium of space. Kaluza suggested that another well-known force, electromagnetism, also works with warps and curves. But Einstein already used space. What's left to work, warp and curve? Well, Kaluza thought, what if there's another dimension to warp and curve? So Kaluza tried to find the equations for 4 dimensions instead of 3. Of course, he found the old equations Einstein had found for the 3rd dimension, but he also found new equations for the 4th dimension. He found that those were the exact equations that scientists had known for electromagnetism for years. However, there are 2 questions that emerge from this though. Does this work mathematically? And if these extra dimensions exist, why can't we see them? The answer for the second question comes in a theory. Imagine there's a ladybug walking on a string. From far away, we see that the string is 2-dimensional, even though we know it's 3-dimensional. However, a ladybug on the string can easily see that the string has 3 dimensions. The theory suggests that we can't see the other dimensions because they're too small, but if there was something the size of those dimensions, it could see them, like the ladybug and the string. The answer for the first question, though, is no, not mathematically. Many scientists tried to make the multidimensional theory work for years, including Kaluza and Einstein, but they couldn't refine it and get it to work. Specifically, they couldn't get the mass of the electron right. Now back to superstring theory. I explained earlier that superstrings are strands of energy that make up quarks. But another question arises with superstring theory. Does it work mathematically? No, it doesn't. With the 3 dimensions we're used to, neither does it work with 4 dimensions, 5, 6, or 7. It takes 10 dimensions and an extra dimension of time for string theory to work. But even by then, why is it so important? Why is knowing we have 10 or more dimensions important? Well, there are about 20 important numbers in this universe, where if there was any tweaking to those numbers, our universe would fall apart. The amount of gravity and the mass of an electron are examples of those 20 numbers. But we don't know why they are the way they are. Here's where the information I gave about the small dimensions come in. Superstrings are so small they can interact with the tiny dimensions, but the dimensions are theorized to be different than we thought them to be. They're geometrical shapes constantly folding, vibrating, and changing. Now, the superstrings will interact, fluctuate, and be affected by the shape of those dimensions. Scientists hope that if they are able to calculate the allowed fluctuations within each of the dimensions, they would be able to calculate those 20 numbers. If these 20 numbers matched up with the numbers which were derived from an extreme amount of hours of experimentation and observation, then it would be the first explanation of why these 20 numbers are the way they are. But how do we know these dimensions exist? And how do we test for the allowed fluctuations in those dimensions? Well, for starters, we can't test for the fluctuations yet, because we don't know the shape of these dimensions. When the theory was first born, there were about 5 candidate geometrical shapes for these dimensions. It was manageable for testing each one at a time. However, over time, more candidate geometric shapes showed up, growing to the thousands. But that was still manageable. But today, not so much, as the amount of candidates have grown to 10 to the 500th power. But scientists are hoping to test if these dimensions even exist through experiments using the Large Hadron Collider, which is under the France-Switzerland border. Scientists hope that if they are able to run particles near the speed of light in a circular path in opposite directions, that when these particles crash into each other, that some of the energy of the debris from these two particles crashing into one another would fly off into another dimension, resulting in a smaller amount of energy after the crash than there was before. In short, string theory is important as it is the closest we'll ever be to the unification of physics, where one theory could describe all the forces and numbers, including gravity.